Hello again, everyone. Welcome to our discussion of section 1.7 in this Math 126 course. So before we get into the details of what the topic is today, I wanted to remind everyone about the best ways of studying in this class, which is skim through the textbook section. About 45 minutes would be excellent. Half an hour to 45 minutes, maybe even in an hour if it's a long section, but definitely not more than 1 hour before I cover it either in these videos or in class. And then after that, attend class and take notes, or watch this video and take notes, and review your lecture notes and solve all the problems that you see me solve without looking at the solutions. And then complete all homework assignments by the due date, and finally review as you go through this course. So this is basically the study plan that I promote because I want you all to end up with an A, with an excellent score in this course. Now, having talked about that, then in this section we will mainly talk about solving linear inequalities. Now, there are several kinds of these linear inequalities. One is just a simple linear inequality, just like the one that you see here, the first one. So that would be just a simple linear inequality. Another type of linear inequality is the compound linear inequality. For example, this one on this page, part D, that's an example of a compound linear inequality. So you have more than one inequality. Okay, let's see if I have other examples of that. No, that's the only one because that's the only one that this section talks about. The other type of linear inequality, these are very, very important categories, are the quadratic inequalities or inequality. So what's a quadratic inequality? Well, that's a quadratic inequality, and any powers of x that are equal, any x to second power, that would be a quadratic inequality. But generally speaking, when you have inequalities where x ends up being a power higher than 1, whether it's 2 or 3, in this case, x times x will be x cubed. Any kind of inequality that you have like that, then it's best if you have the expression shown in factored form. Okay, so we will get to all of this, but I'm just covering the overall set of topics that we will see in this section. And the other one is the rational inequality, just like the one you see here on page 3 of the worksheet. And also this one, it's another rational inequality. Okay, so let me add that to this list. So number 4, rational inequality. I believe we also have, yes, absolute value inequality. Okay, that's the last type of inequality, linear inequality, that we will look at. And also this one, this is a mix of rational and absolute value inequality. So let me add that too, and I will just add it here. and that would be the absolute value inequality. The other reason that I'm listing these is because the techniques to solving each type of linear inequality is going to be slightly different than the other one. So they're all connected. They're all based on a set of specific procedures, but for each type of linear inequality, then you have subtle changes in the procedure. So please make sure that you're aware of which of these linear inequalities you're solving, whether it's on the exam or in the homework assignments, and use that particular procedure associated with that type of linear inequality to solve the problem. Okay, so let's start with this first one. It's the easiest linear inequality we can get. So simply we isolate the x and then solve for it. So here we have 3x greater than 1 plus 2, right? And then we have 3x greater than 3. And then x, divide both sides by positive 3, and we get 1. One of the things that this section wants us to do is not only figure out the solution, but they want us to write the solution using the interval notation, right? So this is the answer, but let's write that answer using the interval notation. So this means x should be anything greater than 1, not including 1, right? Because the inequality symbol is missing from here, from this symbol. So 1 cannot be the part of the solution, but anything greater than 1 can be. So when we want to exclude a number using the interval notation, we always put a parenthesis next to it. So parenthesis 1 means that 1 is excluded. If I wanted to include 1, I would put a bracket, but that's not the case here. So parenthesis 1 comma infinity, and then the infinity side always gets the parentheses. Whether it's a negative infinity or positive infinity, it always gets the parenthesis because infinity can never be included in any interval. It's by definition, infinity is not reachable. Okay, so this is our answer for this problem. Then here's another one, and I hope you're, just like what I've said before, I hope you're pausing the video and writing your own solution down for all of these on a piece of scratch paper, and then coming back to the video to compare your solution, which are far more important than my solution because those solutions represent your thinking, your developing thinking. So those are much more important than these solutions. These are just my thinking, but you're developing your own thinking. So this one, so I'm assuming you already have your solution for this. So we will isolate the x term on one side by moving the 17 to the other. So 7 minus 17, we have 5x less than minus 10. And then x, we divide both sides by positive 5, right? So this would be minus 2. Okay, so to put this in interval notation, this is saying anything less than negative 2 is part of the solution. Anything less than negative 2 goes all the way to negative infinity, right? So we start with parenthesis, negative infinity, comma, negative 2, another parenthesis. Okay. All right, so this one. This is more interesting than the other examples, right? We have more terms to work with. So once again, let's collect all the x terms on the left and all the constants on the other side. So we have 5x, move the positive 8x from the other side, That makes it negative 8x less than or equal to 28 on that side. Move the positive 4 to the other side, it becomes negative 4 as you move it. So what do we have on this side? We have minus 3x less than or equal to positive 24. Okay, now here we got to be very careful, because notice in each of these cases, the part A and part B, in order to solve for x, we had to divide by a positive number. So divide both sides by positive 3, and that didn't change the direction of this inequality. It stayed the same because we're dividing by a positive number. The same thing was true in here. We divided both sides by a positive number, positive 5, and that maintained or preserved the direction of this inequality. But here, this is different, because now to solve for x, what I will have to do is divide both sides by a negative number, right? What this does, it will shift the direction of the inequality symbol from what it is to its opposite. So now it's minus 3x less than or equal to 24. That will shift to the opposite direction, and this side we end up with x, and that side we end up with minus 8. I hope you caught what this dividing by a negative number did to this inequality. It shifted this inequality symbol to the opposite direction. This will happen every time you multiply both sides of an inequality by a negative number, or divide both sides of an inequality by a negative number. In either of those cases, multiplying by a negative or dividing by a negative number, the inequality symbol will shift direction. Okay, so this is one such case. And then we end up with, so this is saying any solution that is equal to negative 8 or larger than negative 8 is part of the solution. So negative 8 is part of the solution. So I'm going to start with bracket, negative 8, comma, infinity. Like that. Okay. Okay, so next one is a compound inequality. So, but the procedure doesn't change, which means we have to, in order to solve for x, we have to isolate x. So how am I going to isolate x when I have positive 9 next to it and negative 2 as a coefficient of it, right? So we have to, in order to isolate x, we need to get rid of the 9, we need to get rid of the negative 2. The technique to eliminating each of these numbers is going to be different. For example, to get rid of the positive 9, we'll have to add positive 9 to all three sides of this inequality. Subtract 9, not add 9. Subtract 9 from all three sides. So minus 9 here, minus 9 here, and minus 9 here. Okay, so we have 1 minus 9 less than or equal to minus 2x plus 9 minus 9 less than 8 minus 9. Okay, so let's simplify. We have 1 minus 9 is minus 8 less than or equal to positive 9 and 9 add up to 0. We end up with minus 2x. Then with this inequality, 8 minus 9, we end up with minus 1. Now what do? We need to isolate x, right? That didn't change. That objective didn't change. So we need to get rid of the negative 2. So how do we do that? We divide all three sides by negative 2. So negative 2 here, divide by negative 2 here, and divide by negative 2 here. Okay, so what happens here? On the left, we have positive 4. What happens here? We're dividing by a negative number, just like the previous example. So this inequality will change to its opposite, like that. In the middle, we'll end up with positive x, like that. This inequality will also change direction to its opposite, like that. And we end up with positive 1/2. Okay? So even though this is correct, it's better to write it so that the smaller number is on the left and the larger number is on the right. So let's do that. So I'm just going to rewrite this. So it's the same thing, but visually it looks better because the smaller number is on the left. So 1/2 less than x, x less than or equal to 4. So compare this with that. It's the same thing, but now the smaller number is on the left and the larger number is on the far right. Okay, so now we have to write this using this answer using the interval notation. So 1/2 is not included in the solution, right? 1/2 is not included because equality is missing. So we have a parenthesis, 1/2, comma, 4 is included. So 4 and then bracket. Okay, that's the solution there. Very, very important, these quadratic inequalities. So with quadratic inequalities, there are infinitely many solutions, and they are very difficult to find. It's very difficult to find what would make x in both of these such that the result of this product is going to be less than 0 or something negative, a negative number. Right? This setup means we want the left side to always be a negative number because it says the left is less than 0. Now, it's very difficult to find what numbers would make that happen unless you have a way of narrowing the solutions down. So we do, in fact, fortunately, have a way of narrowing down the solutions. And that method is first find what would make this left side equal to 0, and treat those solutions as the threshold or boundary solutions. So let's see what I mean by that. So for a second, I'm going to switch this inequality to equality. So I'm going to write, and note, let us find the boundary solutions. These are not the final solutions, but the boundary solutions. In other words, what makes this left side equal to 0? Because we know it cannot be equal to 0, right? But these are boundaries. So the boundaries are nice because we can either include them or exclude them. In this case, we're going to exclude the boundaries because we cannot have the left side equal to 0. So to do that, we say x minus 5 times x plus 1 equals 0. Okay, notice I switched from inequality to equality so that I can find the boundary solutions. Now, using this and the zero product property that we learned about in the last section, 1.6 or 1.5, we learned that. Let's solve this. So we have x minus 5 equals 0. That means that x equals 5. So that's a boundary solution. That's one of them. Then let's find the other one. X plus 1 equals 0. Then x equals negative 1. That's another boundary solution. Okay? So what do I mean by boundary solution? This is what I mean. Right now, we have infinitely many solutions possible. there is not enough time in the world or in our lifetime to sit down and figure out which one of those numbers is going to work out and make this inequality negative on the left. So in order to narrow down that search, we'll do this. We'll find the boundary solutions. Then that boundary solution will divide the real number line into, so this is 0, this middle being 0. And then we have -1, let's say that's that. And we know -1 and 5 cannot be part of the solution, right? They cannot, because these two numbers would make this expression equal to 0, and we are specifically asked to find anything that would make the left side less than 0, not equal to 0, not greater than 0, less than 0. So I'm going to put a hollow circle here. This is -1. And suppose this hollow circle here is +5. Now, I'm going to put a dashed line right on top of each hollow circle. Dashed because those are boundary solutions and are not included in the final solution. So now, instead of checking infinitely many numbers, we have only 3 regions to check. We have to pick a number in this region and see if that number would make this inequality a true inequality. If it does, that same conclusion extends to all numbers on this side or in this region. Then we'll have to test another number in this area. It could be any easiest number in that region. For example, 0 would be the easiest number in this area, right? We could test that here. If that is true, if that number makes this inequality true, then all those numbers in the same region will make the inequality true. On the other hand, if that number does not work out, then none of the other numbers will work out in this region, in this inequality. After that, we will pick a test number in this region to see if that region is going to be part of the solution. So instead of sitting down and spending more than a lifetime, which will not be enough, and test each number in each of the infinitely many numbers in this inequality, instead of doing that, we're just going to test 3 numbers to see what the solution is. And the reason we can do that is because we are able to find the boundary solutions first. So the boundary solutions make this possible. Very, very important to remember. Okay, so let's pick an easy number in each region. So let's test x equals, easiest number in this region would be -2. Okay, what do we get? We get, plugging -2 in that inequality, right? We have -2 minus 5 times -2 plus 1, and we're asking, is that less than 0? We're testing that. So this is a question mark for us. Well, let's see. -2 minus 5, that's -7. -2 plus 1 is -1. Is that a negative number? Is -7 times -1 a negative number? No, it is a positive number. So this question mark now has been answered. So if I write +7 less than 0, you right away know that this is false, right? We picked a test number -2. It led to a false conclusion. 7 is not less than 0. So we say no. That region cannot be part of the solution. So now let's test a number in this region. Any easy number would do. Well, let's test 0, right? Test x equals 0. Let's plug for x with 0. 0 minus 5 times 0 plus 1 less than 0? We're asking this. We don't know yet. We're asking, is the left side less than 0? Then we have minus 5, and then we have positive 1, less than 0. We're asking, is the is the left side less than 0? So let's do the algebra. We end up with minus 5 less than 0. Is that a true statement? Yes, it is. Yes, it is. That checks out. So we say yes. That middle area is a solution. And finally, we have this region to check. So let's pick a number in this region. We're going to test an easy number in that region, which would be x equals 6. Okay, plugging in, plugging in here, 6 minus 5 times 6 plus 1 less than 0. Remember, we're checking. We don't know yet. So 6 minus 5 is positive 1. 6 plus 1 is positive 7. And is that less than 0? Well, that is positive 7. Is that 7 less than 0? No. False. So we picked a test number. It led to a conclusion which is not correct. So we say no. That region is not a solution either. So look at this. And we know that the boundary solutions are also not part of the solutions. The boundary numbers, negative 1 and 5, are not part of the solution because they would make this expression equal to 0, and equal to 0 is not an option. We want the left side to be negative at all times, or less than 0. So our answer is just between all the numbers between negative 1 and 5. So parenthesis, negative 1, comma 5, parenthesis. And the parentheses indicate that negative 1 and 5 are excluded, which you can see with the hollow circle and the dashed line over them graphically. Okay? Okay. Let's go over this one. I'm counting on you that you're pausing the video, solving this problem on your own, and then you come back to the video and see my solution. Please do that if you haven't already. Okay, I'm assuming you've done that, and now you have your own solution. Fantastic. So this is nice because everything has been factored for us. So we can quickly set each of these factors equal to 0 and find the boundary solutions. If this was not a factored expression, we would have to factor it. It would add to our work. So the fact that it's been factored, it makes life easier. Okay, so let's find the boundary solutions. Before we find the boundary solutions, let me ask you this. When we find the boundary solutions, are the boundary solutions going to be part of the final solution? Or like the previous example, they're not going to be part of the final solution? Which is it? Do you think the boundary solutions will be part of the final solution? If you answered yes, you're absolutely correct. In this case, the boundary solutions will be part of the final solution because of this equality symbol under the inequality. So because of that equality, it means that the left side can be equal to 0. So the boundary solutions will be part of the final solution. So let's find the boundary solutions. We have x plus 2 equals to 0. So x equals to negative 2. That's one of the boundary solutions. And then x minus 5 equals to 0. That's another boundary solution. X minus 8 equals to 0. And x equals 8. And that's another boundary solution. Let me make it clear. These are our boundary solutions. Very, very important, because they're going to make this solution considerably easy by dividing the real number line into how many segments? 4 segments. So let's do that. We don't have to draw this graph, but I'm just drawing it to make sure that everyone is following what is it that we're trying to achieve here. So we have the 0 here in the middle. Then we have -2. Let's say -2 is here, and it's the boundary solutions are part of the solution, so I'm going to put a filled-in circle, and I'm going to put a solid line on top of it. Then we have 5. Let's say 5 is here, and I'm going to put another filled-in circle, and I'm going to put a solid line on top of that. And 8 would be here, and I'm going to put a solid line on top of it like that. So we have 4 regions to check. 1, 2, 3, 4. Okay, let's pick a test number, test value in each of these 4 regions. And we're going to do that with the easiest number possible. So let us test x equals -3. And we'll plug that in here to see if the left side is less than or equal to 0. We know it's not going to be equal to 0 because we've already found what numbers will make that equal to 0. But we'll find what makes the left side a negative number. So we have test x equals -3. That would be in this region, right? Then -3 plus 2 times -3 minus 5 times -3 minus 8. And we want to know if this side is less than or equal to 0. Okay, so what do we have? We have, let me put that here, that is -3 plus 2 is -1. -3 minus 5 is -8. -3 minus 8 is -11, less than or equal to 0. We're asking that. Well, all of that means that we have -88, right? -1 times negative times negative, it's going to give us a negative number. 8 times 11, 88, less than or equal to 0. Is -88 less than or equal to 0? Absolutely. So here, yes, this region is a valid part of our solution. So let's test a number here in the middle. And 0 seems to be the easiest number to test. You can, if you like, you can pick 4. It makes no difference. But let's pick the easiest number. Test x equals 0. Then I'm going to plug in with 0 in that inequality. We have 0 plus 2 times 0 minus 5 times 0 minus 8 less than or equal to 0. Like that. So we have 0 plus 2 is positive 2, 0 minus 5 is minus 5, 0 minus 8 is minus 8, less than or equal to 0. Multiply all of those, you get positive 80. Is that statement true? Is 80 less than or equal to 0? Absolutely not. False. So we come here and we say no. That region is not a solution. How about a number here in between 5 and 8? Let's test x equals 6. Right? So plugging in this inequality with x equals 6, we have 6 plus 2, 6 minus 5, 6 minus 8. We're asking if the left side is less than or equal to 0. Okay, what do we end up with? We end up with positive 8, 6 minus 5 is positive 1. 6 minus 8 is minus 2. Right? After that, we end up with minus 16 less than or equal to 0. Is that statement a valid, true statement? Absolutely. It's true, right? So this region, we say yes. That's acceptable region of solution. Now let's test this far right region. And we're going to pick x equals 9. So test x equals 9. I'll try to keep everything on this screen as much as I can. Like that. And then, so plugging 9 into this inequality, we have 9 plus 2 times 9 minus 5 times 9 minus 8 less than or equal to 0. What do we end up with? We end up with 9 plus 2 is 11. 9 minus 5 is 4. 9 minus 8, positive 1, less than or equal to 0. So we end up with 44 less than or equal to 0. Is that a true statement? Absolutely not. Right? False. So because x equals 9 did not work, so this region also is not a solution. So the solution region, according to this, and I'm going to have to move this up so you can see better, the solution region is just here and here. So let's write that up. So the solution, we have to write that out using the interval notation. So the solution is negative infinity to negative 2. When I get to negative 2, should I use a parentheses or bracket? If you said bracket, you're absolutely correct, because in this case, the boundary solutions are included. So that union this piece, 5 and 8, and anything in between. So bracket 5, comma 8, bracket. Oops. Okay, and then let me box that answer right there. So this is the final solution for our problem, like that. Okay, I hope this is making sense. Okay, so now we get to a rational inequality. So with rational inequalities, again, just like the two examples you saw with the parentheses, with the factored terms, like that, just like these two examples, here and here, we're going to have to find the boundary solutions. But the question is, what are the boundary solutions in this case? Because in these two examples that you saw, the boundary solutions were whatever that any number made the expression equal to 0, right? So here, the boundary solutions are two types. One, the same thing. One is any value that would make this expression equal to 0. That's a boundary solution. But the other boundary solution is any value that would make this fraction undefined. That value would be anything that would make the denominator equal to 0. So let me write that down. For a rational inequality, the boundary solutions are 2. Any value that would make the expression equal to 0, And 2, any value that would make the expression undefined. Very, very important. Okay, so let's see what would make this expression equal to 0. Well, any value that would make the numerator equal to 0 would make this whole fraction equal to 0, because 0 divided by anything is equal to 0. So, x minus 6 equals 0, therefore x equals 6. So x equals 6 is a boundary solution. Look at this and think about whether this x equals 6, we know it's a boundary solution, but is it going to be part of the final solution? What would you answer to that question? Will x equals 6 be part of the final solution? If you answered yes, you are absolutely correct. Because take a look at this symbol, inequality and an equality. So the left side is allowed to be equal to 0. And we know x equals 6 will make that happen. Will make this expression equal to 0. So this is going to be, will be, x equals 6 will be part of the final solution. Now, the other thing we need to find is any value that would make the expression undefined. What would make this expression undefined? Anything that would make the denominator equal to 0. So x plus 4 equals 0, therefore x equals to negative 4. So will x we know x equals negative 4 is a boundary solution. We already know that. But will it be part of the final solution? If you answered no, you're absolutely correct, because this will make the denominator 0 and make this expression undefined. So it cannot be part of the final solution. X equals negative 4 cannot be part of final solution. Okay. All right. So let's set it up just like before. You don't have to draw this graph if you don't like to. I'm just drawing it to make it clear what we're doing. So negative 4, let's say something here, somewhere here. And I'm going to put a hollow circle, right? Cannot be part of the final solution. So hollow circle and a dashed line. And 6 will be part of the solution, so I'm going to put a filled-in circle here and a solid line on top of it, and that's that. So how many regions should we check? 3 regions, right? Here, here, and here. So let's do that. So testing x equals, any easy number would do. The easiest number, I think, it would be negative 5. So let's plug it into that expression. We have negative 5 minus 6 divided by negative 5 plus 4 greater than or equal to 0. We don't know that. We're checking. We're checking to see if this statement is true for negative 5 substituted for x. Okay, so let's simplify things. Negative 5 minus 6 is negative 11 divided by negative 5 plus 4. That's negative 1. Like that. Negative divided by negative. That's a positive. That's a positive value, right? So 11. Positive 11 greater than or equal to 0. Is that statement true? Absolutely. So this part is going to be Yes. So yes, this region is part of the solution. Okay. So let's test some value between -4 and 6, and 0 seems to be the easiest one. So test x equals 0. We're going to plug 0 in there, right? 0 minus 6 divided by 0 plus 4 greater than or equal to 0. So that'll be minus 6 divided by positive 4 greater than or equal to 0. This will be minus 3 over 2 greater than or equal to 0. Is that true? Is negative 3 divided by 2 some number greater than 0? Absolutely not. False. So 0, this whole region is not a solution to our inequality. Okay, one more region to check, right? That side. So test x equals some easy number would be 7. And let's plug it in there. Let me move this up a little bit. Like that. And so 7 minus 6 divided by 7 plus 4 greater than or equal to 0. We're checking, right? We're checking to see if this is true. So 7 minus 6 is 1 divided by 7 plus 4 is positive 11 greater than or equal to 0. Is that a true statement? Absolutely it is. Right? This is a positive number, so it's greater than or equal to 0. So again, yes. Okay, so now having identified the solution region, let's write down the final answer using interval notation, right? That's what the problem asked us to. So that region would be negative infinity to -4. -4 cannot be part of the solution, right? We said that. So put a parenthesis next to it. Union 6 is part of the solution. So put a bracket next to it, 6, comma, infinity, and a parenthesis. Okay. Or maybe I should box it with a different color so that they don't mix up like that. Okay, so this one. I hope that you solve these on your own. Again, this is just a reminder. Please solve these on your own on a piece of scratch paper, then come back to the video. Okay? That way, you make sure and I make sure that you're not memorizing my solutions, which are really worthless. I mean that because to you they're worthless because they're my thinking, but you are learning this material in order to develop your own thinking. That's why it's so important that you write down your own solutions before you look at my solutions. So your solutions are much more valuable because they represent your thinking, okay? And you're here to develop your thinking. Okay, so I'm assuming you've done that. You've already written down your own solution and you're here to watch what happens here. Okay, so here we have some expression on the left that is said that we want it to be greater than or equal to 1. Well, let's make sure that we make this easier on ourselves by moving this one to the left and setting the other side equal to 0. Okay, so first we have to take the common denominator here. So 4 plus x over 4 minus x minus 1. So I move this to the left, greater than or equal to 0. Then take the common denominator. 4 minus 6 is the common denominator. And 4 plus x here. Then the denominator here is 1. So, right, the common the denominator of -1 is 1. So in order to make this 1 be equal to the common denominator of 4 minus 6, we need to multiply the numerator and the denominator by 4 minus 6. So that means minus 1 times 4 minus x greater than or equal to 0. And then let's simplify. We have 4 plus x. We have a minus 1 to distribute into these two terms. Minus 1 times 4, minus 4. Minus 1 times minus x plus x divided by 4 minus x greater than or equal to 0. Okay, so we have minus 4 and 4 cancel out. We end up with 2x divided by 4 minus x greater than or equal to 0. Okay, now we're going to solve this for its solutions. Okay, so just like before, just like above, the previous example that we said for rational inequality, the bound or inequalities, this should have been a plural. For rational inequalities, the boundary solutions are any value that would make the expression equal to 0. So let's come back down here. What would make this expression equal to 0? You can see it easily, right? Any value that would make the numerator equal to 0 would make this whole fraction equal to 0. And x equals 0 would make the numerator equal to 0. So 2x equals 0. That means x is equal to 0. So that is one of the boundary solutions. Now looking at this, what we have here, do you think x equals 0? You already know this is a boundary solution, but will it be part of the final solution? Can it be part of the final solution? If you answered yes, you are absolutely correct. It can be, because notice the left side is allowed to be equal to 0. This is one of the reasons we moved the one to the left, took the common denominator to find what makes this fraction equal to 0. Now we know, right? So x equals 0 will make this fraction equal to 0, and it is allowed to be the final part of the final solution because of this equality. The left side can be equal to 0. So x equals 0 will be part of the final solution. Okay. So where is the other boundary solution going to come from? It's going to be, let's look back up again, any value that would be, that's the second boundary solution, boundary solutions, right? Any value that would make the expression undefined. Okay. So looking at this, what would make this expression undefined? Well, any x value that would make the denominator equal to 0 would make this fraction undefined. So let's find what that value is. 4 minus x equals to 0. That means x equals 4. Now, you know this is the other boundary solution. But can this be part of the final solution? If you answered no, you're absolutely correct. This x equals 4 cannot be part of the final solution because it will make this fraction undefined. So cannot be part of the final solution. Okay. Now that we know what the boundaries are, let's plot them and test a number in each region. So we are here, right there. And we have x equals 0, so that's part of the solution. I'm going to put a solid circle on top of it and a solid line right through it. X equals 4, right? So x equals 4, let's say here, that cannot be part of the final solution. So I'm going to put a hollow circle and a dashed line on top of it. So how many regions do you see? We have to check. We have to test 3 regions. Here, here, and here. Okay, so let's test each region. The easiest number to test in this region, and we're going to test here. So let me put that up here. So 2x divided by 4 minus x greater than or equal to 0. We're going to pick numbers in each region and test it in this one. You can test it there. It's okay. You would get the same result, but this is the result we're dealing with after taking the common denominator. Okay, so an easy number to test would be test x equals -1. Plug it in there. 2 times -1 divided by 4 minus -1. And we're asking, is the left side greater than or equal to 0? So we have -2 divided by 4 minus -1 is 4 plus 1, 5, greater than or equal to 0. Is that true? Is this -2 over 5, is that greater than or equal to 0? No. False. Right? So no, that is not a solution region. Let's test a number here. Let's test x equals another easy number, 1. So let's plug it in there. 2 times 1 divided by 4 minus 1 greater than or equal to 0. We're asking if the left is greater than or equal to 0. So that's 2, denominator is 3, greater than or equal to 0. Is that a true statement? Absolutely. 2 over 3 is a positive number and it's greater than or equal to 0. So yes, this region is a part of the solution. And let's test a number in that region, maybe x equals 5. So plugging in here, 2 times 5 divided by 4 minus 5. We're asking if this is a true statement. So we have 10 over minus 1, right? Which is minus 10. So is that a true statement? Absolutely not. False. So this region is not part of the solution. Okay, so let's write the solution based on what we have. So 0 is part of the solution. So I'm going to write bracket 0 comma 4 is not part of the solution. So 4 parentheses like that. Okay. I hope this is all making sense. Okay. All right. So let's move to the next example, which is an absolute value inequality. Right? We have an absolute value inequality. Wonderful. Finally, we got to this. So with absolute value inequalities, in order to solve for x, we will need to remove the absolute value. But remember the absolute value definition that last video we talked about? So let's remind ourselves once again about that. So I'm going to write that up here. So recall the absolute value definition, which says absolute value of x is equal to x if x is greater than or equal to 0, minus x if x is less than 0. That's just a mathematical definition. Why is it important here? Well, because when we solve for x, we'd like to remove the absolute value. Otherwise, we can't solve for x. But look at the definition. The definition breaks up the absolute value into terms that are conditioned. This if means each term, each outcome has a condition. But the nice thing about it is that each outcome does not have an absolute value around it, which means in each of these cases, if we apply the absolute value definition, in each case, we will be able to solve for x, okay? Because there's no absolute value. Look at the right side. Okay, so let's apply the absolute value definition here. One of these is going to be absolute value of x equals to x. That means just remove the absolute value without any more change. So x plus 1 greater than or equal to 1. That's that case for us. That case becomes that for us. The second case, which is that, absolute value of x equals negative x. Negative x is the outcome. So here, on the left, whatever you have inside the absolute value does not get multiplied by a negative 1. So we write that as it is, x plus 1. Then this inequality, earlier in this section, and when we started this video, I said that every time you multiply or divide both sides of an inequality by a negative 1, this inequality shifts direction. So we're going to multiply the other side by negative 1, so this will change direction. So it will be less, from greater than or equal to, it becomes less than or equal to negative 1. This, what happened here, is the application of the absolute value definition. So now we're going to solve from each side the value of x, and we'll determine the final solution based on that. So let's do that. So according to this, we have x greater than or equal to 1 minus 1, or x greater than or equal to 0. That's from this side. And this one, it says x less than or equal to negative 1. Move this one to the other side, negative 1. X less than or equal to negative 2. Okay? So notice what is happening. This one says, let's draw a picture for all of this, because I want you to understand exactly what's going on here. We applied the absolute value definition. Now we end up with two solutions, right? And one of them is that one. It says the solution is 0 and anything greater than 0. So this one says that's the solution. Okay, and let me remember to put the negative infinity to positive infinity here. Okay, this solution says no. The solution is negative 2 and anything less than negative 2. That one says that. Okay, so I want to write a very, very important note here. Note, the individual solutions, these are the individual solutions, that one, do not overlap. If the individual solutions do not overlap, then the final solution for an absolute value inequality is the union of individual solutions. So let me write that down. So the individual solutions do not overlap, therefore let me move this up. Therefore, the final solution is the union of, remember the union and intersection? That's what I'm talking about. Is the union of individual solutions. In other words, the final solution is a negative infinity to negative 2. Is negative 2 part of the solution? Yes. So bracket. Union is 0 part of the solution. Yes. Bracket 0 comma positive infinity. So if the individual solutions do not overlap, the final solution is the union of the solution. Now let me add. Note. When the individual solutions do overlap, the final solution is the overlapping piece. Overlapping segment. Very, very important. This is very important, guys. I hope you take the time to remember this and carefully read this and remember it. So, if the individual, in an absolute value inequality, if the individual solutions do not overlap, which is this case, then the final solution is going to be the union of both solutions, this and that, either this or that or both. That's the definition of the union. And we talked about it, I think the first lesson, section 1.1, we talked about it, I think. That the definition of the union is either this or that or both. And you can test it. I mean, you can test. Once you write down this answer, you can test this with the inequality that we have. For example, pick a number in this interval. Let's say negative 5, right? Plug it in here. Negative 5 plus 1 is negative 4. Apply the absolute value, you get positive 4. Is positive 4 greater than or equal to 1? Yes, it is. Test this interval. Let's say 1. Pick a number in this interval. I just picked 1, right? Plug it in there. 1 plus 1 is 2. Absolute value of 2 is 2. 2 is greater than or equal to 1. Even pick 0. Plug it in there. 0 plus 1 is 1. 1 is equal to 1. So it's still valid, right? But if the individual solutions, once you do this, once you find the individual solutions, and they do overlap. If they do overlap, then the final solution is only the overlapping piece. What I mean is, suppose, just for the sake of making this clear, suppose this arrow went this way and this arrow went that way, right? So we would have an overlapping piece between negative 2 and 0. In such a case, only the overlapping piece would be the solution. So from negative 2, so it would be bracket negative 2 comma 0 bracket. That's if you had this case. Let me make this clear. So suppose we drew this, we had our individual solutions, right? Suppose we had that. We had 0 here and negative 2 here, like that, right? Suppose the solutions went this way, that one, that way, and that way. In other words, suppose we had x greater than or equal to negative 2 and x less than or equal to 0. If instead of what we had that, right? If the individual solutions overlap, which they are here, they're overlapping here, overlapping piece or segment, if the individual solutions overlap, then the final solution will be the overlapping piece. So bracket -2 comma 0. That would be the answer for that. Okay, I hope this is clear. Please make sure you remember that. So if the individual solutions do not overlap, the final solution is the union of individual solutions, which we have here. If the individual solutions do overlap, if they do overlap, which is something I just made up here, these solutions overlap, then the final solution is just the overlapping piece, not the union. It's the intersection of those. Intersection, remember from that section 1.1 in this course, is the overlapping piece. The piece that is common to both solutions is the final solution. Okay, so let's look at this final example in this section. So once again, we apply the definition of an absolute value in order to remove the absolute value symbol, right? Just like this. We're going to end up with two individual solutions if we remove the absolute value. So let's do that here. One solution will be x minus 2 divided by 3 less than 2, right? That's that one. Absolute value of x equals x if x is greater than or equal to 0. Right? The other solution is when in an inequality, the other side gets multiplied by -1. So that would be here, which is x minus 2 divided by 3 without any change. Multiplying the inequality by -1 will switch this to the opposite, and multiply the 2 by -1, you get -2. Okay? So now we're going to find the individual solutions. Let's do that. Here, multiply both sides by +3. Right? So we have 3 times x minus 2 divided by 3 less than 3 times 2. So on the left, the 3 and the 3 cancel out. We end up with x minus 2. On the right, we end up with 6. Then move the -2 to the other side. Then x will be less than 8. So that's one individual solution. Let's find the individual solution on this side. Once again, we're going to multiply both sides by 3 to clear the fraction. Right? Like that. Move the -2 to the other side. It becomes positive when you do that. Or as most of you like to think of it, add +2 to both sides. Either way, it's fine. But I think this is more efficient. So just move things around and remember that you have to change the sign as you do that. So x greater than -4. Right? Okay, so let's plot this. We don't have to, but it's just a graph sometimes helps us better understand where the solution is going. So -infinity to infinity. Okay, then this solution says anything less than 8. Suppose we say that is 8. Notice x cannot be equal to 8, so I put a hollow circle there. So this solution is saying go this way. That's that. This solution says anything greater than negative 4. Let's say that's negative 4 and x cannot be equal to negative 4. So negative 4, and this solution says no, go that way. Those are individual solutions. Are they overlapping? If you said yes, you're absolutely correct. They're overlapping here in this piece between negative 4 and 8. And what did we say about individual solutions that do overlap? What did we say about them? The final solution is the overlapping segment. So what would be the solution here? The solution would be negative 4 and 8 are not included. So the final solution is parenthesis negative 4 comma 8 parenthesis. There. Okay? The overlapping piece is the final solution when the individual solutions do overlap. Okay. I hope that you worked at this with me throughout the video. I hope you started the video with a pile of scratch papers, solved these problems on your own, then unpaused the video and looked at my solutions. If you're doing that, you will do great in this class. Thank you all again for persisting through this video. For now, have a nice day, and I'll see you all next time.